All right, 7-4. Let me just write down what the name of this thing is, and they call it parallel lines and proportional parts. That example that we did a little earlier, okay, when we were going over the questions or the answers to that, that's really going to come into play right here. So let's pop a triangle on here, and let's put the same stuff in that that I showed you earlier. So I'm gonna purposely put this line so it doesn't look like it's in the middle, okay? Because I don't want you to think that it always has to be in the middle for this thing to be true. All right, and let's label it again. A, B, C, and we'll call this D and F. All right. Now, right now, we discussed this just a few minutes ago. Right now, can we say these triangles are similar to each other? No, we can't. But what could we do to make them similar to each other? Make what? Can't say it, Travis.
DF and BC parallel.
Yep. If I made DF and BC parallel to each other, then these are similar triangles. So if they're similar triangles, wish I could see, then let me see what they do. Okay. Give me a sec. AB to BC, E, A, E. Okay. Here's something that, let's do this. Let's call this little segment A. Instead of calling it AD and using 2 letters for all this, let's just use lowercase letters to represent the size. It's just a little bit easier to talk about, okay? So what if I call that A, I call this B, I call this little thing C right here, and this little D right here. So these are lowercase letters, all right? Don't get them the A, B, and C and D confused with the uppercase, okay? So A represents that length AD, C represents that length DB. You follow me? Okay, of what we're doing. So here's what this theorem says. It's theorem 7.5. They call it the triangle proportionality theorem. Now, since I know that these triangles are similar to each other, I could compare this. I could compare A to this whole thing. See this left side of the triangle, of the little triangle, to the left side of the big triangle. So I could, now this is not according to this theorem, but I knew this from before. I could have said, if I compare A, that's the left side of the little one, what's the whole left side of the big one? Is it just C?
A plus C.
It's A plus C. So I could go A plus C, right? And what would that equal? Let's do the right side of the triangle. So the right side of the little triangle. Now what am I doing? I'm comparing the little triangle to the big triangle. Agreed? So the right side of the little triangle is B. What's the whole entire right side of the big triangle? B plus D. Very good. All right. And then what else? I could do the bottom. What do I got? A, B, C, D. We'll call this E, and we'll call this little one F right there. You with me on this? And now I can compare the bottom to the bottom. What would that be? That would just be E to what? E to F. So the bottom of the little one compared to the bottom of the big one. So I know this stuff right here before I even did this lesson. Okay, I didn't have to know anything new to figure out these proportions. I could put numbers in here, obviously. Now here's one thing that we didn't know from before. Let's just change colors on this. Okay, here's something that we didn't know from before, and this is a theorem. A theorem can be proven. We're not going to prove it in class, but if you look at it, they might have a proof somewhere in the book. But here it is. Which you can compare this. You can compare these sides. If these two lines are proportional and they hit these two sides of the triangle, these two segments, A and C, okay, if I compare A to C, now C is not an entire side of a triangle, is it? All right, so it's a little bit different. These are segments of this whole side. All right, so A to C, what do you think that would equal? If I go A to C, what do you think it would equal over here? B to D. Very good. All right, and that's it. That's the new theorem right there. Now, you probably couldn't have gotten that from just the information that we talked about yesterday in class, but that's a new theorem, and they call it the triangle proportionality. I'll just shorthand it, theorem. Okay, I probably wouldn't even remember that name. Every book names things a little bit differently. All right, this book happens to name this theorem that particular name right there. Yep. Yes, go ahead. All right, so that's what that says. So A to C is equal to B to D. And of course, we could put some numbers in here, couldn't we? And let's do that. Let's put some numbers in here. PT. All right, so let's say that this right here is 7.5. And I'm going from the book. And I've drawn my picture just a little bit different. TQ as 3. So let's say this is 3. And this is 2.5. So this is 2.5. I want to solve for A. All right, it's pretty easy if they give you all that stuff. It's easy if you know this theorem. Okay, that's the thing. You got to know this theorem. So if I wanted to solve for A, and I'm given the other 3 sides, I should be able to solve for it pretty easy, shouldn't I? All right, so let's do it. What do I compare? A to what? A to C, which is 2.5, equals what to what over here? 7.5 to what? To 3. And now what do we do with this? Cross multiply. Okay, so what's that? I just made them up. I just said, instead of calling it AD and DB, instead of using two letters to call those segments, I just made it up. I said, let's just call this little a and little b, little c, little d. All right? I just to make it a little easier for us. Don't you think it'd be easier than saying AD to DB equals AF to FC? Just looks a little nicer and a little compact like that. That's the only reason I did that. Okay, so if I cross multiply right here, that's 3a equals what? 18.75. Is that what that is? It's supposed to be a 1 right there. All right, divide by 3. Did you do that? 18.75 divided by 3 and 6.25. All right, cool. And there you go. So the math isn't hard to do, is it? It's just setting it up. And that's the way it's been all year, hasn't it, in geometry? The math has never been that difficult. It's just a matter of taking the geometry, setting it up into the formula that you want, and then you just go ahead and you solve. Okay? You could have set this up a little differently if you wanted to. Watch. Let's see if this would work. I'm just curious to see if this would. What if I compared this side to this side, A to B? Let's see if that would work. So if I went A to 7.5, all right, you see that? I'm going from the left side to the right side this time. So if I compare A to B, how do you think I'm going to compare this down here? C to D. And C is what? 2.5, and D is what? 3. So if I cross multiply, it's the same exact numbers, isn't it? It's the same cross multiplication, so I'm going to get the same exact number. So I could compare it that way if I wanted to. I could go the other way. I could go C to A equals D to B if I wanted to. All right? Let me ask you this. Could I go A to D equals B to C? Watch. If I went A to D equals, what did I say? B to C, right? Could I compare that? Well, let's cross multiply. Let's see if this is the same as this. If I cross multiply this, what would I get? I would get AD equals BC. I should get the same thing here, but do I? Nope, I don't. AC equals BD. Is that the same thing as this? No, it's not. So, and I'm just going to mark it out like that. Can I compare diagonally like this, A to D? No. I can compare the top left to the bottom left segment. You get it? And then I can compare the top right to the bottom right. I could do it like that. I could go backwards. I could go across. I could go from here to here equals from here to here. I could go from right to left, couldn't I? I could go B to A equals D to C. So I could compare it all kinds of ways. What's the only way that I cannot compare them together? Diagonal like this. Okay, I can't compare A to D and B to C. All right, that's really going to come in handy because we're going to have another theorem in a little bit that we're going to kind of look at it the same exact way. All right, so that'll really help you out. Does that make any sense at all? So if they give you 3 of the 4 things, you should be able to find that 4th thing just by setting up a ratio, cross multiplying, working out the math, and getting the answer right there. We good with that? I take that as a yes, the non-response. Okay, we'll see. Okay, I'm going to do this kind of the same thing, but watch. The information that was given was a little bit different. Okay, I was given that these 2 lines are parallel. Agreed at the beginning? And then I could say the sides are in proportion and all that kind of stuff, or those segments are in proportion. What if I did this? Let's just go a different color. What if, again, let's call this A B, C. Oh, I think I changed the letters around, didn't I? That's okay. We'll just keep it like that. It doesn't make any difference. Watch. What if I know this, and I don't know that this line is parallel to this line? You with me on that? Okay, so I don't know that this and this are parallel. I know the line's there. I know it exists, but I don't know that it's parallel. But here's what I do know. I do know that if I compared, if these were numbers right here, okay, pretend they're variables, okay? If these were numbers right here, and I compared A to B, and if that was to equal C to D, right? If I went A to B and that equals C to D, if that was true, if I knew that was true, then what do you think I could say about this triangle, or what do you think I could say about these two things right here? Then that the lines are parallel to each other, okay? So I'll just say parallel, okay, just to shorthand it a little bit. Does that make sense? What did we just do? We've been doing this all year. We had an if-then statement, then we took that if-then statement and we did what to it? We flipped it around, which is the converse of it, exactly right. So the statement itself and the converse, they're both true, right? And so that's what we have. If I know that if I compare A to B and I find out that it's the same fraction as C to D is, then I know that this and this are parallel. If I know this and this are parallel, what does that say about the two triangles? Travis, you said it earlier. They're similar to each other, exactly right. Okay? So I didn't know originally that they were similar, did I? I didn't know that they were parallel, but what did I know? This is all I knew. Okay, they tell me this stuff right here. If this stuff is true, then these two lines are parallel. If these two lines are parallel, then these two triangles, this one right here and the whole big one right here, must be similar to each other. All right, let's move on. All right, here's a triangle. Now it is flashing. Okay, I do see it. All right, what I'm going to do right here is, remember I said on the last one, I purposely didn't want to make it look like it was in the middle. Now this one, I do want to put it in the middle. Is that all right with you? Okay, so the middle would be about right here. So I'm going to take this, stretch it across like this. I don't know if I've talked about this before or not, but so that is in the middle. It's the midpoint. So this point right here is the midpoint of this side. This is the midpoint of the other side. So I'm going to make these two sides equal to each other. Okay. Let me see. Parallel. Okay. So this is the information I'm given. That's all I'm given right there. All right. I'm not going to label it just because due to time. We're running a little short on time. If this line right here connects the midpoints of two sides of a triangle, we actually give it a name, and they call it the midsegment. Just to show you that different books are different, I used to teach out of a book years ago that never gave that the name midsegment. It said this segment right here was the segment that joins the midpoints of two sides of a triangle. That's what they call it. Midsegment's a little bit less to say, so I like the idea that they call it midsegment. But not every book calls it the midsegment. Probably most of them do, but the book I used to teach out of years ago never gave it a name. But anyway, that's called the midsegment. Now, look at this thing. From what we've talked about before, just eyeball it. I mean, I know I tell you not to do that normally, but this line and this line right here, what do you think might be true about those two? Yeah, they're parallel to each other. Exactly right. Okay, they are parallel to each other. Now watch this. This is kind of interesting. If I take this, I'm going to copy and paste it. And let's just make it a different color just so it stands out. Let's go blue. Alright. And watch what I'm going to do. I've never tried this before. I'm trying it now. But it should work if this theorem's right. I'll make it a little bit lower. Whoops. Let's drop it just a little bit lower. Just so you can see the difference. Okay, from there to there. What if I copied and pasted that? What do you think? And I put it right on the end right there. Well, it didn't come out perfect, but
not be directly in the middle of the triangle.
So I need to shift it to the left a little bit.
No, like the parallel line. Yeah, that.
Oh, that's right. That's exactly. Yeah. Thanks. You're absolutely right. Yeah, this thing right here, I just eyeballed this right as far as the midpoint. So it was pretty close, but that's not bad. That's pretty close. Okay, it's not exact, but it's not too bad. What do you think is true about the length of this third side in this midsegment right here? It's twice the midsegment, exactly right. So let's, I wasn't going to put letters in here, but let's do it anyway. It might be easier for us. A, B, C, D, F. Okay, so what could I say about this? I could say that CF equals what? 2 times BD. Would you agree? Or I could go the other way. I could say BD is equal to what? 1/2 of CF. So there you go. That's called the triangle midsegment theorem. How about that? All right, since it's a midsegment and it's a midsegment of a triangle, we call it the triangle midsegment theorem. I don't think we talked about this being half of this. We talked about a trapezoid. Remember, the trapezoid is half the sum of the bases. But this kind of is like that, isn't it? Because the top of this is not really a trapezoid, but you could think of it as a trapezoid with 0 top base, okay, if you want to call it that, right? So it's kind of the same thing, isn't it? So it's taken as very similar to that. I'm glad you remembered that. That's good. All right, I've got one more thing to do, and then we should be finished. Okay, here's the last thing we're going to do, and it's very closely related to what we have been talking about, kind of. All right, so watch. If I have, let's say, a line like this and a line like that. Now that's not a triangle, is it? And let's go this nice purple. Why do I keep doing that? Okay. Now watch this though. All right. So that's a nice little horizontal line. I'm hitting the shift key. Do you know what the shift key does? Okay. So what it does, it makes it so it's parallel to this. And I'm gonna purposely put a big old gap in here like this. What do you think's true about those 3 purple lines right there? They're parallel. Okay. I purposely made them parallel to each other. But look at the segments that they cut off. Look. Do you see from here to here? From here to here, that's a segment, isn't it? And from here to here, that's another segment. Now, they're not segments of triangles, are they? Because this is not a triangle. Now, eventually, yeah, they'll touch, but they're just 2 lines cut by these 3 transversals. Let me do this real quick. Watch. If this is A and this is B, this is C, this should be intuitive because of what we did before. How do you think we can set this up? I could set up what? A to what? To B equals what? C to D. Or I could do what? A to C equals B to D. Or I could go the other way. What's the one way I cannot go? I can't go diagonal. I can't go A to D and C to B. All right. Let me give you some problems to do so that you can practice these on your own. So it's 10 to 27. All right, and it's pages 489 to 491. All right, and it's section 7.4. There you go. Have fun with that.